In this video, we're going to continue the process of proving Brooks' theorem. Last time we explored the basic properties of critical graphs, and this time we're going to focus on a particular case, the case of two connected graphs. So we're going to examine what does Brooks' theorem look like in the case where the graph in question has a two-vertex cut. All right, so let's go ahead. So recall the basic statement of the theorem that we're trying to prove is that if we have a simple connected graph, which is not complete and not an odd cycle, then the chromatic number, the number of colors you need to give it a proper vertex coloring, is no more than capital delta of G, which is the maximum degree of a vertex. And again, the strategy we're following is from a proof of Lovács as communicated by Bondi and Murty in their textbook, arguing by contradiction, etc., as we discussed last time. But what we're going to do is explore some particular properties of critical graphs that are going to help us. So remember from before, a graph is called k-critical if it has chromatic number k, but if whenever we remove an edge, the chromatic number drops. Now, I should mention that that is not exactly the standard definition. Almost equivalent to it though. The standard definition is that a graph is k-critical if its chromatic number is k, but the chromatic number drops for every proper subgraph. So not only removing edges, but also potentially removing vertices. These are the same notion if you have a connected graph. I mean, because when you remove a vertex, it's either an isolated vertex, in which case your graph wasn't connected, and maybe these are different, or the vertex was connected to some other vertex by an edge, in which case when you remove the vertex, you also remove the edge, and the chromatic number will drop in either case. So, but we're going to, have use of both of these definitions, and that really doesn't matter because we're assuming the graph is connected. So from now on, the graph in question will always be connected, and we can phrase the concept of being k-critical either in terms of removing edges or just removing anything, looking at a proper subgraph of any sort. All right. So let me just recall, not from last time, but from even before that, that you can always color a graph if you are allowed to use more colors than the maximum degree of a vertex. And that's a very kind of simple kind of inductive proof where each time you want to color a new vertex, as long as you have more colors than the degree, you can always pick a color that's that doesn't contradict anything that that vertex is connected to. Now, the Brooks statement is that you can do one better, and that's what we're actually trying to prove. But interestingly, for critical graphs, there's you have this inequality not just with the largest degree, but with the smallest degree of a vertex. So the theorem that I'd like to briefly mention is that if you have a k-critical graph, then it's not only k-colorable, which it has to be less than capital delta, but it's actually it's not only the chromatic number of k, which is less than capital delta, but it's actually less than or equal to little delta plus 1. All right, so let's explore this theorem quickly. So suppose you have, the little delta is the minimum degree of a vertex. So we suppose we have such a vertex of minimum degree. And let's just suppose, by contradiction, that degree is strictly less than k, where k is, you have a k-critical graph. Now, because you're k-critical, you know that if you remove that vertex, then you have to be k-1 colorable. Okay, so let's imagine what's going on. So we have our original graph, and we have some vertex v. It's connected to some other vertices by some edges. We remove v, and now we know that that you can k-1 color that graph. On the other hand, because the degree of that vertex was delta, which was strictly less than k-1, the neighbors of that vertex v are in number at most k-2, because the degree was at most k-2, strictly less than k-1. And that means by using just that k-first color that we haven't used among its neighbors, we can add v back in and give it a reasonable coloring. In other words, if we could do this, then we could color G using k minus 1 or fewer colors. And that would have told us that the chromatic number of G is less than or equal to k minus 1, but G was k critical, so its chromatic number was k, and therefore it wasn't k minus 1 colorable. That contradiction is what we were aiming for, and therefore we've proved the theorem. Okay, so now for the next result of interest, recall before we showed that if you have a k critical graph, then it can't have any cut vertices. It has to be a so-called block, non-separable. Now, what if instead of removing one vertex and making it disconnected, what if you could remove two and get it disconnected? Could you find such things? The answer is yes, but finding such a pair of vertices that gives you a true vertex cut turns out to be very restrictive if you have a k critical graph. All right, so what we're going to show is the following proposition, which kind of just rolls off the tip of your tongue, right? Here's what it says. If you have a two vertex cut in a k critical graph, u and v being the vertices that when you remove, it becomes disconnected, then the sum of the vertices, the sum of the degrees of those two vertices has to be at least 3k minus 5. Okay, so that's the proposition. Now, you might ask, if you think about this statement, well, some natural questions. Is this good? Is that like a good number for the degrees? Is that, and like, why? Is it useful? Why should we care that we can do that? So let me answer both of these questions in turn. First, like how good is that? You know, I mean, the previous proposition says that the degree of any vertex has to be bigger than the minimum degree of a vertex in the graph, and it has to be at least k minus 1. That's what we showed a moment ago for critical graphs. Each vertex has degree have at least degree k minus 1. So u and v both have degree at least k minus 1, so the sum of the degrees a priori would be at least 2k minus 2. But what we're saying is something much stronger. You know, instead of being 2k minus 2, it's 3k minus 5. It's like a lot bigger. The total degrees are pretty big, you know. In other words, if you can cut your graph, your critical graph, by removing a couple of vertices, those two vertices are going to be connected to a bunch of stuff. That's kind of what this says. So that's, I don't know, it's curiously strong, this proposition, you know, it's good in that sense. Okay, but perhaps more interesting to us is it useful? And for us, the important thing is going to be, if we have such a cut, we're actually going to be able to prove Brooks' theorem. And here's why. If you think about it, twice, so, you know, Brooks's theorem is just going to say that, you know, is just going to say that that k is no more than capital delta. That's what we're aiming for. We're aiming to show that the chromatic number is no bigger than capital delta. Well, twice capital delta is at least as big as the sum of the degrees of these two vertices, which by this statement is at least 3k minus 5. Now, previously, we had examined k critical graphs in small cases. We had looked at 1 critical, 2 critical, and 3 critical graphs, and in each of those cases, we had deduced that Brooks's theorem must actually hold. And so, so for that reason, well, I guess we didn't totally state that it held for those, but we will state it. You know, the only interesting thing is going to be k critical for k at least 4. So now for k at least 4, 3k minus 5 is at least as big as 2k minus 1. Just check that. And so, well, that means that twice the biggest degree is at least 2k minus 1. Now, twice the biggest degree is an even number. So to have an even number bigger than an odd number means that the even number is actually bigger than that even number, which is just 2k, which is 1 bigger than that odd number. And that tells us that the delta is at least k, and that's Brooks' theorem. So if we had this bound, we would know Brooks' theorem if you have a 2-vertex cut. So what comes next is just an examination of why this proposition holds. So let's pause, take a deep breath, gather our wits about us. And now let us proceed to the proof of the proposition. So to prove this proposition, we're going to really have to dissect everything that happens in this case when you have a k-critical graph and a two-vertex cut. So let's see what's going on. If you have a two-vertex cut, then, well, you remove those two vertices and your graph breaks up into a bunch of components, h1, h2, up to hl, let's just say. Okay, what can we say? Well, I would like to take those components, look at the vertices that are in them, and then think about the graphs that I get by looking at those vertices, adding in u and v, and looking at the edge-induced graph, vertex-induced graph corresponding to that. This is actually not a weird thing to do. Let me draw a picture so you can see. So let's suppose we have our original graph, and I have my u and my v. So in this case, what am I doing? I'm going to remove u and v, and I'm going to get a couple of components in this case. Maybe in general, I would have more components. Here, I've removed u and v, and of course, you have to remove all edges that are incident to u and v, and you get some couple of subgraphs there in this case. And now what I'm going to do is I'm going to look at the graphs that I get by taking each of those bits, each of this bit and that bit, and adding in u and v and the corresponding edges connecting it to those components. So what we get in that case is we get these couple of graphs. I'm viewing both of these as subgraphs of my original graph. So what I do is I take these things, the h1 part, I add in u and v, and that gives me all this stuff kind of on the left. And then I can take h2, these two guys, I add back in u and v, put in all the edges that you got, and you get these two subgraphs. So g1 and g2 are a couple of subgraphs of my original graph, which basically correspond to the pieces that you get when you remove u and v. These are kind of like the analogs of the blocks that you get when you remove cut vertices. So now that we've identified these subgraphs GI of interest, let's examine how colorable they are. So on the one hand, because G was k-critical, and these are proper subgraphs, they're strictly smaller, you know that they're each k-1 colorable. But now let's think how those colorings are going to interact with these vertices, u and v. So for example, let's suppose it was possible to color each GI such with k-1 colors, because they're all k-1 colorable, such that in each of these colorings, u and v have the same color. Well, in that case, we could shuffle the colors on each component, each GI, to make them agree at those two colors, those two vertices, and we'd be able to color our original graph with k-1 colors. But that can't be true because the chromatic number of original graph is k. What if it was possible to color each of these components with k-1 colors, giving u and v different colors? Well, then again, we could shuffle the colors and get a coloring of our original G. So what does that mean? It means that that there's at least one of these components that they're such that every way you color it, you have to give u and v the same color, and some other component such that every way you color it, they have to have different colors. Okay, so there's some component G1, one of these subgraphs G1, such that every k-1 coloring gives u and v different colors, and there's another G2 where every k-1 coloring gives them the same colors. Now, if you think about what that means that if you think about G1 union G2, well, it's k-colorable because it's a subgraph of a k-colorable graph. On the other hand, it's not k-1 colorable, because if you were able to k-1 color it, then you would you would be able to k-1 color both the G1 part and the G2 part with k-1 colors. But the only way to do that is to make the colors both agree and not agree at u and v, so that's impossible. Then again, if you look at anything smaller than G1 union G2, remove any edges or something like that, then that would be a proper subgraph necessarily of the original graph, and therefore it would be k-1 colorable. Therefore, this thing is k-critical. Of course, that just means it has to be the original graph, because that every proper subgraph would have to actually have chromatic numbers smaller, right? Okay, anyways, so So there we go. Actually, what does that tell us? That tells us that that there's only two pieces. This L, which was the number of pieces, is actually 2. And these two pieces of the property, the first one, every way to color it with k minus 1 colors has u and v having different colors. For G2, every coloring gives them the same color with k minus 1 colors. Okay. Now, in particular, let's notice that means the vertices u and v are not adjacent, right? If you can give it a proper coloring in G2 and u and v have the same color, then they can't be adjacent. Okay. So now again, L is 2. So we really have this picture, H1 and H2 are the components of G of v minus v, and we have these G1 and G2. Oh, and that should not be a G. This an H. This should be a G. Okay. So let me observe that G1, if I identify u and v, it's not k minus 1 colorable. Now, G1 is the one where u and v have to have different colors, right? And similarly, if I take G2 and add an edge connecting u and v, then that's not k minus 1 color. Remember, G2 is the one where u and v are required to have the same color, right? If a k minus 1 coloring gives them the same color and you add an edge, you can't k minus 1 color it anymore. And similarly with the other case. All right. These are G's, excuse me. In fact, okay, but not only is it k minus 1 color, is it not k minus 1 colorable, it is k colorable. And in fact, we'll actually show that it's k critical, which will be a great kind of result. Basically, it says that if you have a 2-vertex cut and you break it up into these 2 pieces, then they're both kind of critical themselves, which is kind of interesting. They're not, they're close to things that are critical, where you either identify or connect those two u and v. Okay, anyways, let's move along. So first off, I want to show why is it k colorable if you squish those 2 vertices together. So of course, you knew that the original graph G is k colorable, but this is not a subgraph of the original graph G. This is, you take a subgraph and then you squish 2 vertices together. That's just something different. Why should it be k colorable? Well, on the one hand, if you remove both vertices, it's k minus 1 colorable. But what does that mean? U and V are not adjacent to each other. So if I take that kth color that I haven't used and just assign that to u and v, well, that's different than anything that u and v are adjacent to, because I haven't used that color. And they're not adjacent to each other, so that doesn't, it's not a problem that they have the same color, because they're not adjacent. And so therefore, you get a way of coloring G where u and v both are assigned the same color. But a coloring of G where u and v have the same color is really a coloring of what happens when you identify those 2 vertices together. And in particular, you get a coloring of the subgraph where those vertices are identified together. All right. In fact, we are going to show that it's k critical. In other words, we want to show that if you have any edge, for example, and you remove it, then that's k minus 1 colorable. Well, the edges of this graph are really correspond to the edges of G1 with these things identified is really just the edges of G1, because those weren't connected by an edge, u and v, so you didn't get rid of any edges by squishing them together. All right. Well, you know that on the one hand, G was critical. So you remove that edge and there's a k minus 1 coloring. And then you use that coloring to color G1 and G2. And what do you know? Well, if you restrict that coloring to G2, well, G2 had the property that whenever you k minus 1 color it, u and v get the same color. But that means in that coloring, because u and v have the same color, if I look at it over on the G1 side, I get a coloring of G mod uv. All right. So something similar happens on the other side. In fact, it turns out that G2 plus UV, when I add that edge on the other side, I get something K critical. Again, what do we need to show? We need to show it's K colorable. And this is simply because, well, you remove one of these vertices, it's K minus 1 colorable. I can stick that thing back in with a Kth color, and it's, doesn't contradict any of the coloring that I've chosen prior. So I get a K coloring, it's K colorable. But I want to also show that if I were to remove an edge, it would be K minus 1 colorable. Well, in this in this G2 plus HV, plus UV, excuse me, I have one special edge, the UV edge, and then I have the other edges. If you remove the UV edge, then of course you have a proper subgraph of G, and because G was K critical, this is K minus 1 colorable. Okay, so it's so this is K colorable when you add that vertex U back in, and then all these H to G's, excuse me. Okay, now if you have an edge which is not that new edge, but it's just somewhere else, and in other words, corresponding to an edge in the original G2, well, you know that when you remove it again, your original graph is K minus 1 colorable. And if you again look at that K minus 1 coloring and restrict it to G1, you get a K minus 1 coloring of G1. And you know that in G1, every time you K minus 1 color it, U and V have to be assigned different colors. But that means that when you look at it back on the G2 side, it doesn't hurt to add that edge back in, plus UV, right? You add that edge back in on the G2 side, and it still gives a coloring because the colors for U and V were different. Adding the edge doesn't give a problem. Okay, so there we go. So to summarize, we have these two components. If you look at the subgraphs G1 and G2, and you either identify U and V or add U and V respectively, these are both K critical graphs. Now, the previous result tells us that the minimum degree of a vertex for a K critical graph is at least K minus 1. And so on the one hand, you know that you have these vertices U and V in the graph G2 plus UV, a K critical graph, and their degrees have to be both at least K minus 1. Now, what does that mean in terms of the original graph? Well, in the original graph, you had, so G2 is a subgraph of the original graph, having some of the edges emanating from U and V. We have this new edge, UV, and so when we're doing this degree count, one of the degrees on each side, for each of these guys, one of these degrees in the K minus 1 count, or in the potential K minus 1 count, corresponds to the edge UV. So in other words, in the original graph, each of these vertices had to have at least K minus 2 edges that are accounted for in the subgraph G2. Now, I guess the critical point here is that there are no edges in common between G1 and G2. So that's something that I'm implicitly going to be using, but so you should think about that a little bit. If you don't immediately see that, go back and you can think about it, it's true. So now in the bit G1, well, again, you have this new vertex UV. Its degree is at least K minus 1. Now, in the original graph, those K minus 1 edges emanating from this new UV correspond to edges emanating from either U or V into the graph G1. And therefore, we get K minus 1 edges accounted for by the UV vertex in this graph. Altogether, this gives us a total of this plus this many edges, which is 3 K minus 5 edges emanating from either U or V in the graph G. And that's the proof of our proposition. All right, so to be continued next time.